Now just imagine we've got this rod that's zipping around like this, and at that moment right there, that brief moment, we know how fast the center of mass is going. Suppose it then hit into something in a perfectly elastic collision. Then we've done those problems. Then that object will then, whatever it hits, is going to go shooting along a surface. So if I had a surface there, and something waiting to be hit, so that gets hit, and then I take it down a ramp. We've done that problem. And then it's going to hit something else over here, which is going to do it a perfectly inelastic collision. And then, of course, we'll stick a spring on the end. Yes?
Are we to assume that the string that's wrapped around the smaller bit, are we assuming that it's wrapped around and can keep going down and keep
Yes.
expanding?
Yeah. We would have to. And I think in the original problem, I made some comment that assume that this will continue to accelerate within the duration of the problem.
So on the test, there was a problem like that, and then plus the momentum problem?
Yeah, it was one long problem. Basically, 15 parts. In an ideal situation, I could just look at their last answer and pretty much know if the rest of it was right. It was the easiest one to grade too, because they just look at, oh, they're off by a number here, let me just type in, I had a spreadsheet, let me type in the number here, and then automatically changed everything else. So I could. The students were not as enamored of this test as I was, but it is one of my favorite tests. All right, questions at the moment? All right, let's take a break, stretch legs, we'll come back. Because in this problem, the spring is attached to a string, and the spring is going to oscillate back and forth and create a frequency, a sound. Thus, the test is Rube Goldberg plays a note. So we need to talk about that piece of it.
So when is matches 16, 17, I think is the.
It's right now scheduled for Tuesday.
Yeah, but the test is Tuesday, so is it still?
No, the multiple choice test is Tuesday. The calculator test that would employ that stuff is Thursday of next week.
So it's still Tuesday.
All right. Yes, I never done this before. I turned on the video. Let's talk about waves. The two that we care about are longitudinal and transverse. There are some textbooks, I don't see it a whole lot, but some textbooks which will also talk about surface waves, and then there are electromagnetic waves, which is 150, physics 152. We're more interested in mechanical waves. These are mechanical. Because they require a physical medium in order to actually move, to propagate. And there used to be a slinky in here. Oh, something else I should have done during that break was go grab some props. I will be right back. I'm just going to let that run and grab a slinky and a foil.
It's losing. We had a biology teacher, he just visits.
That's why I wear long sleeves too.
It's just because our school doesn't have.
Almost prepared for football, you got like the socks.
Aaron tried telling me that one year was like some,
I got a shower when I get home. Last night, I was going to right after work, but then I just fell asleep on accident, so.
I've never noticed before, but on a box for the Slinky, it tells you how to play with it in your hands. Hold end of coils. Oh, original Slinky with both hands. End coils. That's a big difference. Now raise and lower each hand in a rhythmic motion. I know that's not what they intend, but that's the way it's written. All right, so the big difference between a longitudinal and transverse wave is how the actual particles move. So if I got a Slinky here, I'm gonna let go of some coils at the top. Let's see if we, is that more visible there or more visible against the dark?
Probably against the whiteboard.
I'm gonna release some coils at the top. What do you notice?
There was a wave shot through it.
Okay, and, all right, so we have a wave that went down to the bottom and then reflected. What actually moved down to the bottom? Is Ethan the only person who saw anything?
I saw it, it went.
Okay, what actually went down to the bottom? Because this coil right here did not travel down to the bottom.
does energy travel down, the kinetic energy travel down?
You can make that argument, that's not what I'm shooting for. Thinking more physical.
That last coil went down one because you had your coil up there.
That last coil.
I don't know how to say it, but one coil went down a little bit farther, you released the coil up there.
Okay, so recognize what's moving here is that this is pushing against the next coil. What you're actually seeing is several coils close to each other, a higher density of coils. So it pushes the next coil, which pushes the next coil, which pushes the next coil, and so on and so on. The coil, once it's pushed, will then bounce back, thus pulling back on the next coil, which had already gone down. And as it's a longitudinal wave, the particles move parallel or anti-parallel to the wave. The wave went down and back, and the coils basically moved in the same direction or opposite direction. A transverse wave, you were about to demonstrate. Get into a position where you can actually stand up. Don't stand up yet, just get to where you can stand up. It works so much better if everyone's participating. All right, we're gonna do a stadium wave. We're gonna start on this side right here, so you three are gonna stand up and down, and when they stand up, then the next group, and so on. You ready, Janet? Whenever you three are ready.
I'll count it down.
Sure.
You want me to do it?
Yeah.
3, 2, 1.
That is a transverse wave. The wave moved that way, but you, as the particles in the wave, just moved up and down. You move perpendicular to the wave. So particles move, that's move, not more, move perpendicular to the wave. We'll just touch on surface wave. A surface wave, in an ideal sense, if you're thinking about an ocean, if you look at the particles in an ocean, if I have a wave that's traveling in essence, a particle there is going to travel in a circle. which means that there's part of the moving in the direction of the wave or opposite direction of the wave, the longitudinal piece, and then part of it's moving perpendicular, so a transverse piece. So a surface wave, in essence, is just a combination of these two. And I bring it up only in case you run across it someplace, but we will not presumably talk much about that from now on. So an example of a longitudinal wave is I'm going to call it the slinky pulse. Now there's another wave that all of you have experienced, actually you're experiencing right now, because all it needs is one particle to hit another particle, which is another particle, which is another particle, which eventually hits your eardrum. Sound is a longitudinal wave. In geology, we're about to go, basically, I'm going to expose almost all of my geology knowledge. When there is an earthquake, say there's an earthquake here, and over here we have some sort of seismograph. As it shakes, you got ground basically pushing against, there's some rubbing going on and there's some pushing going on. So there's part of this thing that goes shooting through, go through the Earth's core and eventually reach the other side. They will get there first. They are primary, that when there's an earthquake on the other side of the world, these are the first waves that hit, the longitudinal waves. They are primary, or you could also consider them pressure waves. Either way, geologists call them P waves. Now, one of the reasons why the P waves get to us first is they can go straight through the Earth. There is a liquid core here, and condensed plasma core. There's non-solid in the middle. And longitudinal waves can travel through liquid, gas, plasma. They can travel pretty much through any of this stuff. So that is how, one of the reasons we know that whatever's in the middle here, it's not a vacuum, because they can travel through it. Likewise, there are other waves that can't go through the middle. Think about if you're in a bathtub or in a pool, if you put your hands in the water and then you lift your hands up, you don't see this ripple effect running across the pool. It might have a little bit of an effect right then and there, but it's not like you're dragging water with you and you see this huge wave going like this. Transverse waves don't go through non-solids particularly well. So the transverse waves have to go around the long way. So they get their second or secondary waves, or they're considered shear waves, because in a shear wave, if I have a medium like this, shear force is one that pushes sort of perpendicular to the grain, causes objects to tilt. So an example of a transverse wave is an S wave. Or we can also demonstrate it with a long coil here. If the wave is traveling that way, that's better if that's anchored. See how well I can do this without screwing up. I might do this for that. Daniel would be so kind enough as to hold that. So another example of a transverse wave, as it goes towards him and back, I'm going to pull harder. Please don't let go. Now notice that what's happened here is as I pull up on it, this coil pulls on the next coil, which pulls on the next coil. I bring it back down, and then starts pulling the other coils back down. So So in the transverse wave, these objects are moving this way, but the wave is moving towards Daniel and back. All right, now you can look over here. Thank you. I'm just going to say long coil wave, for lack of a better term, with battle ropes. Are you familiar with battle ropes? Sometimes in gyms, it's just a long rope attached to the wall, and yeah. Transverse waves, you're doing transverse waves if you do that. It'd be very difficult to do a longitudinal wave. I guess you'd have to push. All right, basic types of waves. The way that we would actually write it, if I drew a wave looking like that, for a transverse wave, that could actually be a physical representation. That if I took a snapshot of the coil as I sent a wave towards Daniel, it physically look like it's going up and down.
Could that also be a depiction of compression over time in a longitudinal line?
Yes, it can. And that's what I was heading towards. That if I'm dealing with, say, sound, in reality, now I will use the term air molecules. I do recognize that air is not a molecule itself. Air is composed of many different types of molecules, primarily nitrogen, oxygen. I think argon's number 3. Okay. Argon's number 3, so someone's going to contest it. But if I have So if I really were trying to draw a sound wave, this would be a more realistic idea of what it is, where I've got places where the molecules are close to each other, places where they are farther apart. This would be known as compression. And where they are farther apart and less dense than the atmosphere around, this is known as rarefaction. It was like rarefaction, but pronounced rarefaction. And so it's just a series of compression and rarefaction. In the case of the slinky, there are places where the coils are close to each other, compression, or stretch a little bit farther apart, rarefaction. If I wanted to represent that in a more convenient way, going to sort of Coy's comment, I could draw a peak where it is high compression, and then a trough where it's low compression, high compression, low compression, high compression. So I can use the same diagram as you mentioned for either type of wave. Now, let's say I've got a barrier here, wall, and I send sound towards it. What's going to happen when the sound hits the wall?
It's gonna bounce.
What's the official word for that?
Echo.
That's sort of the result of it.
Reflect.
Yeah, it's going to reflect. So the wave's going to hit the wall and it's going to bounce off of it. So that means they're going to have a wave going this way and a wave coming this way. They're going to come across each other. What happens when waves meet?
Compression.
Pardon?
Compression.
Maybe.
Do they start bouncing off each other?
I missed what you said.
Do they start bouncing off each other?
It depends upon how you want to, if you want to look at it from a particle point of view, then potentially. If you want to look at it from a wave point of view, it's probably not the best way of doing it.
Those two waves run into each other at the beach.
All right, so let's see if we can narrow this down a little bit. All right, so if I have a wave that's traveling to the right, and then a wave traveling to the left.
Whenever they meet, do they create a bigger wave that goes like higher than the
original two
In
waves.
this situation, yes indeed, they would. So when they meet, the two waves are going to combine. That is, blanking right now. It's called the principle of superposition. Where I got two objects that will just will, in this case, add to each other. This will create a bigger wave. And when it creates something bigger than it started with, this is known as constructive interference. And then they will pass through each other. So if I have small wave and big wave coming towards each other, they will meet to create something bigger than either of them, and then afterwards, the big one keeps going, but the small one keeps going. Now if I have a wave on opposite sides, what will happen?
Destructive interference.
Yep. Characterized by something smaller than what we started with. And so, if they are the same size, there'll be a moment where it's perfectly flat, and then they'll pass through each other.
Always canceling.
So if I have a sound that is destructively interfered, let's say it's just about to hit your ear and it's complete destruction, what would you hear?